Hello guys, welcome back. Today we will talk about elliptical wing for those who ask me. Okay, so first of all, I will start to showing you my reference books, which are this one and this nice book. Okay, as you may know, elliptical wing is the best wing configuration that an aircraft can have. I will not go deep inside the technical and aerodynamic advantage, but just I will show you a picture which tell us that in an elliptical wing we have the area distribution is uniform and the load distribution is the same as the area distribution, and also the stall of the wing is simultaneously. If you see the rectangular wing, the load distribution is different from area distribution, and the stall starts at the tip and goes to the root of the wing for strongly tapered and so on. So the main advantage is that the stall here is simultaneous. It is not from the tip to the root whatsoever, because in this case you will have a loss of lift. In this case, the loss of lift is lower, as you can see. So this is the main reason that elliptical wing is better. Then go ahead and good, as this part is better. Then having an elliptical wing says all but says nothing. I mean, there are different types of elliptical depending on the geometry and also on the position of the quarter chord line. So it's up to you to choose the better. I will show you later how to build the most common. Then you have to use your skill and improvise. As you can see, the important one of the main difficult disadvantage of elliptical wing is that construction. So in the past year, studies show that it is more important to have an elliptical load distribution rather than elliptical wing form. So there are some approximations, as you can see, and also this is valid, this technique and also this one is valid to calculate the aspect ratio of a pure elliptical wing, which is here shown, because in an elliptical wing it is very hard to determine the chord, the tip chord and the root chord. So this technique is very useful. For as I told you before, it is important to have an elliptical lift distribution. This means that the lift is elliptical. For a rectangular wing, this is not true, but shaping, tapering and so on, you can have something that can recall the elliptical lift distribution, as you can see here. So how can calculate it? With the lifting line theory. As this 5.14 refers to the chapter of this book, which I showed you before in the previous video, which is very useful to study some concept about aircraft design. Okay, the technique depicted in that book tells us that you take the wing, divide it in 7 on what else stations. This is our station, and then you apply all these formulas. I will not go deep inside. If you want to read this, you stop the video and read. Otherwise the YouTube time is less than study time. And after all the application of these steps, you will go to this graph, which is the solution of this problem. Determine and plot the lift distribution for a wing with the following characteristics. This plot is calculated using a script from Matlab, which is here, and I will show you why this is not an elliptical lift distribution, because as you can see, the semi-span location, the lift on the wing goes to 0 at 7 meters. So what you have to do is to change some parameters here on every parameter in order to get the lift distribution 0 at the tip of your wing. Here you have to have lift equals to 0. So how this script work? Applying the formula I showed you before. This one. We will run the script. As you can see, the lift is 0 at 10 meters semi-span location. If I modify the surface and we will go to 30, you see it goes between 8 and 9. If we change the aspect ratio to the half, we will go. We are having a loss of lift because this wing is 10 meters. Okay, I will close someone. The code will be in the comments. I will copy this code for you and will be in the comments of this video, so you can just copy and paste and just start to play. Okay, so how we will do an elliptical wing with Solidworks? This is the big question, and this is why you are watching this video, because nobody told you that. Perfect. Okay. I found an article talking about the Spitfire, the Vickers Spitfire wing, and says that the elliptical wing is a union between two ellipses, and at the quarter chord. Oh, sorry, there is something that is not working. Okay, I will show you just the first one. Okay, where are we? Okay, How I did this? This is very simple. First, you make a sketch, top plane, ellipses. We will have 50 and to 100. There is not a ratio between these two dimensions. I mean, it's up to you. It's not in military. It is very hard to find very detailed information about a wing or something, because these are covered by military secret in the past, so they are not available now. But I will. This is what I understood. Okay, so we have 100. Okay, so then you will put a vertical wing here in order to avoid some jokes that Solidworks make. Then there is a ratio. Yes, of course, there is a ratio that a rule, not a ratio, a rule that tells you that. Oh, sorry. That tells you that the center of the two ellipses, this difference, this distance, should be 2 to 1, or in some other papers or documents says that this point should be a quarter, from quarter to 0.3 or to 25 to 30% of the chord. So it's up to you. Then you will make another ellipsis. No, sorry. In this case, okay. Then you will trim this. Then you will erase this one, and you will have points. Okay, oh, it's not a problem. Okay, so now you have your elliptical wing. Then what you have to do, oh shit, well, I will then what you have to do is divide your wing in stations. Okay, so this is done easily, drawing every single line. I will show you just one because YouTube time is very short. So you start from here, and then start from here, from here. You choose the span, you choose how many, you choose everything. It's up to you. There is not a rule for this. Once you have this, you will trim all the exceeding lines, and then you will measure every single line. Okay, and you will have something like this in the end. I chose 100 millimeters in span, and the first one is 200 because here it is supposed to have the fuselage. After you have measured all this line, you will need to make a Excel file which will oh no, sorry, this. Okay, as you can see, I took the coordinate from the Clark key. I call Clark, but it's Clark Y profile, which is this one. And then using Excel, I make station 1, station 2, station 3, station 4, 5, 6, 7, and 8. And then I multiply the coordinates for the value given here. You see? This one. Second station, this value multiplied by the value given here. The third station for the value given here, and so on. These are the chord of the station which I calculate here. Sorry, I will close something because this code is going very heavy. Don't save. These are the chord of the stations I calculate from Solidworks, and as you can see is A1 multiplied by sheet coordinate tag, and you have all the coordinate for the airfoil at station 3. Then what you have to do, this chart change, you will need to add this one plane per station, and then you will insert every airfoil in every plane. I will show you another file. This part 2. Okay. I made an offset because when you will build an elliptical wing, you need some reinforcement on the leading and the trailing edge, some reinforcement and guide. Okay, so as you can see, there is a plane and there is an airfoil in each station. Okay, so you will need to repeat. This is very time consuming, but you need to do this at all the stations from the root to the tip. Okay, so I will show you the last one. As you can see, this is taking a nice shape, as you can see. This is perfect. Oh, I have some misalignment here. I will need to move. Please check this. But if you have something like this, is not a problem here, because you will take this airfoil separately, not just an assembly in the real life. So when you will glue this part, you will have the chance. So, but this is not a problem. It's not a problem to us. Okay, this is the most interesting part that some of you ask me. This is a surface loft, and this is very easy to make. You will need to do two lofts, to the upper surface and the lower surface, but remember that for Solidworks, surface has zero thickness. This means that if you want to make some CFD, the flow will pass the surface, will not follow. You will not see the stall or the lift, or so the flow will just pass through. If you want to make something like this, there are two ways. You can make the wing solid without the surface loft. So you will loft from this rib to this rib with just a solid wing, or you can make a 1 millimeter thickness contour or offset, and then you will loft that surface. Okay, so this is very nice, and in the end this is what you got. I left just one here to show you. Remember that you will need some you will need the space for the spar, which should be with angles, not a circular, not a tube, but a geometry with an angle, because if you make a spar with a circular tube, you can have the rotation of the airfoil along the spar axis. So try to choose the right geometry here. See the previous video for this issue. In case you will need to make this elliptical wing with some flaps and some ailerons, the technique is the same I show you in the previous episode, which I think is, I don't remember, maybe 4 or 5. Yeah, 4. In episode 4. So you will need to shape all the aileron, all the airfoils, in order to make the room here. And also, as you can see, there is no twist here. So if you need to make a twisted wing, you will need to follow this technique for the elliptical wing, added the twisted wing technique, and also if you want to make some dihedral of the wing, you will need to add to the above two techniques the third, which I did in the, I think is episode maybe 3. Yeah, maybe 3 or 4 or 5, I don't remember. So anytime you want to add some a feature, watch the video and try to use your skill to merge the technique of the video inside this one in order to get what you want. That's all, and I will show you. want to show you just that this is a surface loft. If I edit, you see, these are the points, these are the guideline. There are no guide curves. It's just the contour, the edge of the airfoil going from the root to the tip, to the root to the tip. Always when you are doing a loft, check the zebra or the curvature, but better the zebra stripes, because you can have the touch, you can see the shape of your loft, but in this case it's just an aesthetical thing, because for Solidworks surface loft has zero thickness. So thanks for watching, and I hope that this video can help some of you.